Okay, today we will solve 5 easiest problems from AIME 1995. Let's start with the first one. The first one will be very simple. We have several squares, so they're located like this. You see the picture. And the first square is 1 by 1. So here S1 is a square with the side 1. And the length of the sides of the square SI plus 1 are half of the length of the sides of the square SI. So as you can see, I plus 1 is the next index, I is the previous index. It means that the sides of each next square are the halves of the sides of the previous square. So if the first square is 1 by 1, the next one will be 1 over 2 by 1 over 2, the next one will be 1 over 4 by 1 over 4, and so on. And two adjacent sides of the square SI are perpendicular bisectors of two adjacent sides of the square SI plus 1. So two sides of each previous square are perpendicular bisectors of the two sides of the next square. And in the picture here, you can see what they mean. This side of this square is a perpendicular bisector to this side, and here we can mark angle also 90 degrees, and this side is perpendicular bisector to this side, and we can mark it like this. This side is a perpendicular bisector to this side, and this one is perpendicular bisector to this one. So this is it. And of course the pattern continues, and they are interested to find the total area covered only by the first 5 squares. So S1 and up to S5. You will find this total area covered by the first 5 squares in the form of fraction m over n, and you need to provide the answer what would be m minus n, numerator minus denominator. This is it. So the problem is very simple, and we can even make a picture in this case, because we have finite amount of squares. So the first one, the largest one, the side is 1, and then the next squares will be located like this. So here comes the next square, and here we will have the next one. It's not probably up to scale, we just make a picture for our convenience. It's not necessary to be like very precise. So just to draw 5 squares here, let me make this one a little bit smaller, and so we have 5 squares like this. So let's mark what would be the sides of these squares. So the first one has a side 1, this one has the side half. The sides of the next square, the length, are the half of the sides of the previous square. So this green one has the length of the side 1 over 2, and we can use it like green color here. Why not? To make it obvious. And here the length of the sides are 1 over 4, this length of the sides are 1 over 8, and this length of the sides is 1 over 16. Great. And here let us use orange color. And you need to find the total area covered by these 5 squares. Of course, what you want to do right away is to add the areas of these squares in total. But of course, they have intersections. And here, for example, this small square, it's in intersection of this one, and it will be counted twice, because when you add this area and this square counted twice. And you don't want it to be counted twice, you want it to be counted only once when you calculate the total area covered by squares. So this one should be subtracted eventually, because you added 2 times, so minus this square. And what is the area of this one? Well, it's obviously that this is a perpendicular bisector, and this small green portion is 1 over 4. So it's 1 over 4. And the area of this square is easy to calculate. What would be the area of this square? Well, it is the square with the side half of 1 over 4. It will be 1 over 8, this small square. And what is the side of this small square? It is a half of 1 over 8. It's 1 over 16. And what is the side of this small square? It is the half of 1 over 16. So it's 1 over 32. This is it. And now we understand what we need to do. We need to add up all these areas of these squares and subtract these small squares, because each of them is counted twice. So let's calculate. The area of this orange one is 1, plus the area of green one is 1 over 4, plus the area of this purple is 1 over 16, plus the area of this black one is 1 over 64, plus the area of this red one is 1 over 256. Perfect. Let's subtract these smaller squares. This small square has a side 1 over 4, so it will be 1 minus 1 over 16. This one has a side 1 over 8, it will be minus 1 over 64. This one has side 1 over 16, so it will be minus 1 over 256. And this has a side of 1 over 32, it's minus 1 over 1024. Very important that this 32 is 2 to the power of 5, so the square would be 2 to the power of 10, and that's how we get here 1024. And what can we do immediately without trying to add all these numbers? So we can immediately cancel out some elements here. So this cancels out, and eventually you end up with a very simple expression that looks like 1 plus 1 over 4 minus 1 over 1024. So this sum is 5 over 4 minus 1 over 1024. And let's calculate this difference. So let's find the common denominator. 4 is 2 to the power of 2, and 1024 is 2 to the power of 10. The common denominator is 2 to the power of 10. So this fraction, first one, should be multiplied here and here by 2 to the power of 8, 2 to the power of 8, because in this case 2 to the power of 8 will be a common denominator. So it will be 2 to the power of 8, 5 times 2 to the power of 8 minus 1 equals, what is 5 to 2 to the power of 8? 2 to the power of 8 is 256, and if you multiply 5 by 256, you will get 1280. 1280 minus 1 divided by 1024, and it equals 12791024, and it is your final answer. So it is the total area enclosed by these 5 squares, and you need to find it in the form of fraction, which we did, and you need to, the answer would be numerator minus denominator. So let's look at this fraction, and it is m over n, and numerator minus denominator would be 255, and it is the correct answer for this problem. So let's go to the next one. Okay, let's solve the next one, the equation number 2, and let's look at this one. So find the last 3 digits of the product of positive roots of this equation. So you have an equation, you need to find its roots to solve it, and to multiply these roots to find its product and to get the last 3 digits of this product. But of course the main issue here is how to solve this equation on the first place. And if you take a look at this one, and you can ask yourself what makes this equation so unusual. And of course the right answer is this power with logarithm, because if this number here is like a normal number, simply like maybe 8 or 10 or even 15 over 4, something like this, in this case you can solve this equation immediately. But unfortunately here we have a power of logarithm, which complicates the situation. And of course, if it is a problem for you, you should think immediately, how can I get rid of this power? And the common technique looks like this. If you have log base AB, how to get rid of this log? You should make a substitution. So instead of b, you get a to the power of n. So for the power b, you should adjust some number n such that this one will work. And in this case, this logarithm turns into an, which is simply n. It is the main idea. Of course, we can go into more detail when it's possible, but in this case, how to get rid of this one? So log 1995x. So if x is 1995 to some power of t, then this log will be simply equal to t. Very simple. But the only question, so if this one will look great, will the other terms of our equation look great? Because this substitution may be very good to get rid of this logarithm, but with the other parts we will have some mess, and the equation will look even worse sometimes. So we should check if it's a good substitution here. And let's also answer quickly a question why it is possible to do like this. Well, x is 1995 to the power of t. What does it tell you? Well, it tells you immediately that x can be only positive number, for any t, and can you get any possible value x by like running t through some interval? Well, obviously, if t belongs from minus infinity to plus infinity, then this value runs over all positive numbers. So in this case, x can be any positive number. So this substitution is like possible. It is normal because we consider only positive roots of x. Positive roots of x, by the way, x equals 0, you can see immediately that it is a root of this equation. It is not considered, so we consider only this one, and without loss of generality we can tell that in this case, if we have a positive x, then for every positive x there exists some number t such that x equals 1995 to the power of t. What number of t will it be? Well, it will be log 1995 of x. It is t for a certain x. It's just, I mean, you can skip these details. You can simply say that you have this substitution. We just wanted to justify it a little bit. Okay, so in this case, let's solve this one, 1995 square root. So instead of this power, you will have t times x to the power of t equals x square, and x square, we will leave it like this. So finally, instead of x, we will substitute here this value, and we will have here square root of 1995 times 1995 to the power of t, and again to the power of t, equals 1995 to the power of t squared. Just remember, when you have power in power, for example, if this one is 2, and in the power to the power of 3, and in this case powers are multiplied, and in this case you will have 1995 t squared, because it's t times t. And this one, square root, is nothing but 1995 to the power of 1 over 2. And it is this one. And on the right side, we will have 1995. These powers are multiplied. It will be 2t. Finally, our equation looks like this. These powers will be added. 1995 to the power of t squared plus 1 over 2 equals 1995 to the power of 2t. And these two numbers are equal only if these powers are equal. And let's solve the equation that looks like this: t squared plus 1 over 2 equals 2t. And it is a simple quadratic equation for t, and t squared minus 2t plus 1 over 2 equals 0. Let's multiply it by 2, not to get these fractions. 2t squared minus 4t plus 1 equals 0, and we will quickly solve it for t. Discriminant is 16 minus 8 equals 8, and therefore square root of discriminant is 2 square root of 2. Then t equals 4 plus minus 2 square root of 2 divided by 4. And we have two possible values of t. T equals 1 plus 1 over square root of 2. So this one, I just separate, I divide them separately, this one by 4 and this one by 4. This one by 4 will be 1 over will be square root of 2 over 2. But if you divide it once again by square root of 2, you can get it in this form. So, and finally, 1 minus 1 over square root of 2. So these are two possible values of 2. And finally, let's go back to our substitution. Let's remember that we were looking actually for x. We were looking for x, and x is 1995 in this power. So x should be equal 1995 to the power 1 plus 1 over square root of 2, or x is equal to 1995 to the power of 1 minus 1 over square root of 2. And these are two different roots of your equation. So we solve the equation. Of course, the good solution implies that when you found these values of x, you go back to your equation and you actually check that it works for you, because you should never leave it like this. So when you get two values, two solutions, you obviously should go back and to check that both of them work. Well, and I will leave it for you because it's very easy to substitute these values to this equation and to check that both of them work. And eventually, you need to find the product of these positive roots, and you need to find the last 3 digits of this product. So if you multiply these roots, the good news for you that when you multiply them, these powers will add to each other, and this 1 over square root of 2, it will simply cancel out. And it means that x1 times x2 simply equals 1995 to the power of 2. It is the product of your numbers. x1 times x2 is simply 1995 square, and if you square 1995, I'll multiply it, and you will find the last 3 digits of your product. Well, let's quickly multiply it. It will be 5, 2, 45 plus 2, 7, 4, 49, 4, 9, and here 5 times 9 is 45, and here we have 4, 85, and so on. But here, well, how many digits do we need? 2 or 3? Let me check. Unfortunately, the last 3 digits. So here we have to continue. 5 times 9 is 45. Here we get 4. 9 times 9 is 81. Plus 4 is 85. And here we have 8. And here 9 times 9 is 81. Plus 8, 89. And here 8. 1 times 9 is 9, 17. Something like this. So, and eventually, well, unfortunately, here we will have 45 again. So this is it. This is enough to get the last 3 digits, this part. I just don't want to multiply them completely. So it will be 5, 2, 1 is here, 0. Okay, and eventually there will be something else. And your answer is 0, 25. Of course, you could do it in a different way. If you need to find the last 3 digits, maybe for you it will be easier to represent 1995 as 2000 minus 5, and this product would be, this square would be just this expression squared, and you can write it as like 4 million, because it's a square of this one, minus double product of this, minus 25. So it's just, it depends on you how you calculate. I just did it in a straight way, and the right answer is 0.25, and it is the answer for this problem number 2. Okay, let's solve geometry. Geometry number 4. It will be a very interesting problem, and so we have here several circles, 2 small circles like this one, and one larger. So circles of radius 3 and 6, this is 3 and this is 6, they're externally tangent to each other, as we see, and they're also internally tangent to a bigger circle of radius 9. And here we have a common tangent line, which is a little bit extended, and now it is a chord of a big circle. And you need to find the length of this chord. And the problem looks very simple, very straightforward. 3, 6, bigger one is 9, this one is tangent, extended, and you need to find the length of this chord. So how should we solve this problem? Well, before we start solving, very important thing that I need to remind you. When you have, for example, 2 circles that are tangent, for example, like this one, and another circle like this one, immediately you should mark that 3 points always belong to the same line. And the points is the center of a big circle, the center of a smaller circle, and the point of their tangency. These 3 points always belong to the same line, like this. And if, for example, you have circles that are externally tangent, like this one, like black one and green one are externally tangent, it is exactly the same situation. So the center of a big circle, the center of smaller circle, and the point of their tangency are always belong to the same line. It is a very important thing, and you always use this fact when you solve problems on geometry related to circles. Here, let's look closer at our picture. What can we tell? Well, at first, this circle and this circle, they are externally tangent, and it means that this center, and the point of their tangency, they belong to the same line, right? Okay, do we know now the position of the center of this big circle of radius 9? At the moment, we have no idea. Of course, it looks like this is a diameter, and it looks like the center of the big circle is located somewhere here on this diameter, but we don't know for sure yet. So the best scenario here is to maybe mark it somewhere here, because we don't know yet the position of the center of the big circle. So let's mark this point O, and we assume that it is the center of a big circle. What do we know? That this point, these 2 centers, and the point of tangency of a small circle and big circle, they belong to the same line, right? So it is the same line. And let's mark here distances. For example, this radius is 3, this total radius is 9. It means that this part here, let's mark it, it is 6, OA is 6, this one is 3. By the way, this is 6, this is 3, and this center of a big circle, this center of this circle and the point of tangency also belong to the same line. So let's connect them like this, and let's mark here that this is 6 because it's a radius of this circle, and this one should be 3 therefore because this is 9. And if you look at this picture, when you marked all the centers of your circles, for example A, O and B, you will immediately see that here we have a problem. And the problem is the next one. In this triangle BOA, this 3, 6 and this is 9. It means that the sum of two sides, BO and OA, is equal to another side BA. And in any triangle, there is a basic thing that is called like inequality of triangle or triangle inequality, that the sum of two sides, the sum of any two sides is always larger than the third side. A plus B is always larger than C in the case if you have a non-degenerate triangle. Non-degenerate, it means that these three vertices of triangle, they do not belong to the same line. Only in the case when three vertices of triangle belong to the same line, like this, in this case you have a degenerate triangle, and in this case the sum of two sides equal to the third side. And here you have exactly this case. So it contradicts to the fact that BOA is not a degenerate triangle. It means that the only way where we can have this situation is when O is exactly on the segment BA. When O is on the segment B, we will not have any problems, because if O is here, it means that this segment will be 3, this segment will be 6, and the total sum will be 9, and here this side BA also will be 9. In this case, there will be no contradiction, but so O should be on BA. And it's a very significant fact, and it means that we should redraw our picture separately, and now we can mark the center of a big circle on a segment, and it will greatly simplify the solution, okay? So let me separate it here. Now we know very important fact, that if we connect these two centers, the center of a big circle will be located just somewhere here. O. And by the way, of course, it also shows us that, for example, if you connect O and B, this point of tangency will be on this line, so we can extend it a little bit. If you connect O and A, two centers, this point of tangency will be also on this line, so eventually like this. And of course, it is all on the same line. So for example, we can mark these points X and Y, and because this line passes through the center O of a big circle, of course it is a diameter. So now we have like a complete understanding of the situation, and we justified why O is between A and B on the same segment. Of course, this is 9, this is 6, so it means that this is 3 and this should be 6, because this is 9 and this is 3. And what else do we need to mark? Of course, when it's a tangent line, you always have to connect it to the center of the circle. The center of this circle with radius 6 is A. So, and we have to make a connection like this. So this one is a perpendicular, and of course this one is 6. And it is a tangent line to another circle. Therefore, we make this radius. This is 3. Okay, so here we have a trapezium, and you obviously well, if you have an experience in geometry, you recognized probably here the very well-known problem in geometry, very simple one, when you have just two circles and they are tangent externally like this. So let me draw a little bit better another circle. So we will draw it like this, and you need to find the length of the common tangent line. So here's a common tangent line, and you need to find its length in terms of radiuses of your circles. And the solution is always 2 geometric mean of radiuses of this circle. So if this is R and this is R, then this common tangent line, this portion of it, is 2 geometric mean of RR, which is very easy to show. But however, here it will only help us to find this portion, and we don't know what is this one and this one. So maybe it's a good approach here to find this one. It will be, in our case, 2 square root of 6 times 3. This segment is 18, or it will be 6 square root of 2. You can mark it like this. However, there will be a question how to find this one and this one. So very important thing, we need to use somehow the fact that this point and this point, they belong to the big circle. At the moment, we don't have any means to define the position of these points. Really, it's a very significant thing. This point is located on this circle, but in this picture we do not mark it in any possible way, because now this point has no difference between maybe this point and this point. We have no idea what is like the position of this point. Somehow we need to connect it with other elements of our picture, and the only way to mark that this point is on the big circle is simply to connect it with the center of the circle. So to mark that this one is 9 is just like the obvious and necessary step. You can't solve problem without it. And the same thing here, we have to connect this point with the center of the circle and to tell that this one is 9. Great. So 9, 9, what's next? Well, obviously your chord that you are looking for is the side of this triangle. Let's mark it M and N. O, N, M is your triangle. It is isosceles triangle. This is 9, this is 9, and you are looking for this chord. Well, it would be amazing, for example, if you could know this angle. In this case, you would find MN by using like cosine rule, but in our case, you can't find this angle. It's just not obvious how to get it. Well, what else can we know? So if you look at the geometry here, you will quickly notice that this figure is a trapezium, and this is 3, this is 6. The position of point O on the lateral side is well defined because it is 3, it is 6. Basically, you know everything about this trapezium. You can find this lateral side, the position of O is defined, and obviously you can find this altitude, this perpendicular, because it's parallel to the basis of your trapezium. The position of point O on the lateral side is defined, and you will have no problem to find this perpendicular H. And what does it mean for you? If you find this perpendicular H, it is an altitude in your triangle MON. And what do you know? You know this side is 9, you know H, and after that, by using Pythagorean theorem, you will be able to find this segment. And in another triangle, this one, this is 9, this is H, and you will be able to find this segment. And after that, the problem will be solved. However, let's find H from this trapezium. And in order for us to solve this problem like faster, we can separate this trapezium and to draw it right nearby. So let's make a picture. We have a trapezium. It looks like this. Two of its angles are 90 degrees. So this is 90, this is 90, this is 3, this is 6. And here the position of point O. This one is, this segment is simply 3. And another one is simply 6. Perfect. And we draw this perpendicular here. And we are looking to find H. Obviously, there are many ways to solve this problem. For example, you can extend lateral sides of trapezium and to use like two similar triangles that will appear, or like similarity of triangles. But there is even a simpler way. For example, you can make a perpendicular like this one. And after that, of course, you notice that this figure that is separated is simply a rectangle. This one is parallel to this one. So this portion of H here, it is equal to 3. This one is 3. And what about this other portion of H that you have on the left? Let's mark it as X. You see here, because this one is parallel to this side, here you have two similar triangles. This triangle is similar to this one. What would be this base of triangle? Well, 3, 3, the total is 6, so it means that this is 3. And let's also just delete 6, and we'll simply mark that this is 3. So from this triangle and this one, from similarity of these two right triangles, we can write X over 3 equals leg over leg equals hypotenuse over hypotenuse. It will be 6 over 9. And from here, X equals 2. So X equals 2, 2, 3. It means that H, this perpendicular, equals 5. So let's delete here H. And instead of H, we will simply write 5. Therefore, from this right triangle, by using Pythagorean theorem, this leg is 9 square minus 5 square, and this leg from this right triangle is also 9 square minus 5 square, and the total length of the chord MN will be 2 square roots of 9 square minus 5 square. Well, let's calculate it. 81 minus 25. So 81 minus 20 is 61 And of course, we should not forget about minus 5, so it will be 56. So the result is 2 square root of 56. It is the real chord Mn, the length of Mn. What do they ask us in this problem? They ask us to find the square of the length of this chord. So the length of this chord is 2 square root of 56, and the square of this number is simply 4 times 56, which is 224. And 224 is a correct answer for your problem. So this is it. Okay, we'll solve problem number 5, which is a very simple problem on algebra from AIME. So let's look at this one. For certain real values a, b, c, d, we have an equation, certain real numbers, a polynomial of the 4th degree with real coefficients equals 0, and this equation has 4 non-real roots. Basically, it has 4 complex numbers that are roots of this polynomial. The product of 2 of these roots is 13 plus I, and the sum of 2 other roots is 3 plus 4i. Well, and you need to find this coefficient b. So let's remember the basic fact, and even the condition of this problem. It even pushes you to remember a simple fact. If you have a polynomial with real coefficients, and in our case it looks like this, x4 plus ax cubed plus and so on plus d. There is a polynomial with real coefficients, and there is some complex number, let's call it x1, which is a root of your polynomial. So x1, such as f of x1, is 0. If it is true, then x1 conjugate is also a root of your polynomial, and it should look like this. Polynomial with real coefficients, x1 is a root of your polynomial, f of x1 equals 0, then x1 conjugate is also a root of your polynomial. I will not go here into details about like complex numbers, about polynomials. It's I assume that you know it, and we will not spend like extra 15 minutes in like explaining it, but it's very easy to prove just like a simple problem on algebra. So, and of course we will use this fact here because this polynomial has 4 non-real roots. It means that one of these roots is x1, and inevitably some other root should look like x1 conjugate. x1 conjugate. For example, some other root is x2, and it means that another root inevitably should look like x2 conjugate, which means for us that these 4 non-real roots that they talk about, they must look like this: x1, x1 conjugate, x2, x2 conjugate. So these are pairs of conjugate complex numbers, inevitably, just because of this fact. The product of 2 of these roots is 13 plus I. Okay, so let's ask a simple question. Is it possible that the product of 2 of these numbers is 13 plus I? For example, x1 times x1 conjugate. If x1 is a complex number, it looks like m plus if. Conjugate number is symmetrical with respect to real x's, and it looks like this. The product of 2 of these looks like m square plus f square if you multiply them, and it is always a real number because m and f are real numbers. And in this case, the product of this is a real number, and there is no way that it looks like this. No way. It means that when they speak about the product, for example, it should be different numbers from here, whether it's x1 times x2 or x1 times x2 conjugate. Yeah, something like this. Well, I would like to write that x1 times x2 is 13 plus I. Well, does it make any difference if I write, for example, that x1 times x2 conjugate is 13 plus I? Is it possible for me just to leave it like this? Well, in general, yes. I can assume that all numbers here are not conjugates. And it's very simple to understand why. If, for example, the product of these 2 numbers is 13 plus I, then you need to remember this fact, that I can assume, I can redenote, I can rewrite our numbers, because x2, I can simply rewrite, for example, as x3, and in this case, x2 without conjugate, it will be x3 conjugate. It will be like this, because instead of this number, I can assume that it is an independent, like separate complex number without conjugation, but this another root, x2, will be this one conjugated. So it means that here I can just redenote, rewrite this expression as x3, and another one will be x3 conjugate, because we have a very simple property that if we take x2 conjugate, it will be back to x2. very simple property with complex numbers. I hope you understand what I mean here. It's a very simple thing that we can assume that when we consider the product of two numbers, that there are no conjugation signs here. So let me delete some part here and we will continue. So the product of 2 is 13 plus I, and the sum of other two is 3 plus 4i. So let's write that the sum of other two, which should be x1 conjugate plus x2 conjugate, equals 3 plus 4i. Well, immediately you know that the sum of conjugates is a conjugate of the sum, so it will be equal x1 plus x2 conjugate equals 3 plus 4i. So, and this is it. Immediately what comes to my mind, that if this complex number x1 plus x2 conjugate is 3 plus 4i, from here I can immediately deduce that x1 plus x2 is symmetrical with respect to real x's, and it should be 3 minus 4i. And that's what I can get from conditions that I have. This one is essential, this one is essential, and of course this one is essential. Okay, so what do we know? That we know our polynomial has 4 non-real roots. It means that our polynomial can be represented as the next product. So let's write it. So here on the left side we have a polynomial x1. Unfortunately, we will have to write all of it plus bx squared plus cx plus d. And on the right side, it can be represented by using its roots like this: x minus x1, and is the first root, times x minus x1 conjugate times x minus x2 times x minus x2 conjugate. It is just a basic thing from algebra, right? You can represent the polynomial in this way if these numbers are its roots. Here should be the coefficient a, but in our case, this coefficient a, it's like first coefficient here. It is 1 simply. Okay, so we will go straight to solution. We need to find coefficient b. Coefficient b is a coefficient near x squared. Near x squared. And here, if you consider what would be the coefficient with the x squared, it will simply look like this. For example, if I take the product of 2 of this x squared, then later it will be multiplied by x2 times x2 conjugate. It's x squared multiplied by this. So next, what should be else? What can be else? These two, if I multiply x squared, what would be the other coefficient? It will be plus x1 conjugate times x2 conjugate, and so on. So basically, you consider the pair of any of these two parentheses, like for example this one and this one. And when you multiply them, here you will inevitably get x squared. And if you multiply it by another two of the parentheses, you need only to consider the term here that doesn't contain variable x. So it should only contain this one and this one. So the product of these two contains x1 times x2. And if you multiply it by x squared, it will be in addition to the coefficient that will eventually, you will see near x squared. And after a while, you will quickly understand that the total coefficient near x squared, it will look like this. It will consist of 6 different summands. So it will be like this. So x1 conjugate plus x1 x2 plus x1 x2 conjugate plus x1 conjugate x2 plus x1 conjugate x2 conjugate, and finally plus x2 conjugate. It's just we found out what is this coefficient just by understanding how these parentheses are multiplied and what would be the total amount of total coefficients near x squared. When you sum them all up, here you will have x squared, and in front of x squared you will have this expression. And let's look closer at this sum. What do we know here? Well, at first, this product x1 conjugate x2 conjugate, it is simply conjugate to this number. So this one equals 13 minus I, right? It's very simple. And what with other numbers? For example, this one is simply 13 plus I. 13 plus I, it's this number. 13 plus I, so we know two of these. And what can we tell with others? With others, we can simply group them. For example, we group this one, and x1 stays in front, and in the parentheses, we get x1 conjugate plus x2 conjugate. And we grouped here two of these, and let's also group two of these. So two of these, and here we will have x2, x1 conjugate plus x2 conjugate. And finally, this sum can be rewritten as x1 plus x2 times x1 conjugate plus x2 conjugate, which is simply x1 plus x2 times x1 conjugate, x1 plus x2, all of that conjugate. Okay, so in total, what is the total coefficient near x squared? So we don't need not to forget that we also add two of these. The sum of these two is 26 plus product that looks like this. This sum x1 plus x2, we already know that it is 3 minus 4i, 3 minus 4i, and this x1 plus x2 conjugate is 3 plus 4i, 3 plus 4i. And if we calculate it, we will simply get the value of the coefficient near x squared. So this is we calculated by using the formula for difference of squares, and 26 plus 9 plus 16, and this is 25, and 26 plus 25 equals 51, and 51 is totally the coefficient near x squared. This is it. So the problem is pretty simple. You just need to know the basics of algebra, and this one is solved. Let's go to the next one. Okay, and our final problem for today will be the problem number 7, and I chose this one because I consider it to be pretty simple, and we are solving 5 simplest problems from every AIME paper. So you know that 1 plus sine t times 1 plus cosine t is 5 over 4, and 1 minus sine t times 1 minus cosine t is some fraction m over n minus square root of k. You know that these numbers k, m, n, all of these numbers are positive integers, natural numbers, and m and n are relatively prime, so this fraction m over n is already in reduced form. You need to find this sum m plus n plus k to sum all these numbers. Well, if you start solving this problem, you can immediately notice that this expression looks very similar to this expression, and it's a great point. But however, even the more important thing that this expression that you have here is simply an explicit equation that you can use to find t. It's a trigonometric equation for t. And the first idea that I have, for example, when I see problems like this, maybe I will be able to solve this equation for t, and then to simplify t here and to find this expression. It will be just ideal way. So let's start from this one. We will solve it, and of course it's a good idea to start from expanding this parenthesis. We'll have 1 plus sine t plus cosine t plus sine t times cosine t equals 5 over 4. Cosine t equals 5 over 4. Of course, we bring 1 to the right side, numbers to numbers, and we have sine t plus cosine t plus sine t times cosine t equals 1 over 4. That's an equation that we have here. If you have a lot of experience in trigonometry, you will be able to solve this one pretty fast, but some people, I would tell most of people, they can't solve these equations like right away. And if you're stuck at this point, maybe you will be able not to solve completely this equation, because really what you need to find here is this expression. And let's understand how it looks. Maybe it's organized in this way that we don't need to solve this equation completely. Maybe we just need some information from it. So let's look at this one. If we expand here, we will get 1 minus sine t minus cosine t plus sine t times cosine t. And as you can see here, this expression is what we need to find. And that's what we have. when I see this expression and this expression, immediately what I would like to do is to add them right away. Because if I add them, this one cancels out, this one cancels out. But in order to add them, of course, I can't just add this one to this one. I should add also right side to the right side. So we should introduce some variable here, a, that it is the value of this expression. And if we add them up, what we have? Sine, cosine cancelled out. And on the left side, you will have 1 plus 2 sine t cosine t. And on the right side, you have 1 over 4 plus a. And eventually, this one, of course, you recognize the formula sine of 2t. And you get an equation sine of 2t equals a minus 3 over 4. What information does it give you? The information that you can get from here, that as soon as you know sine of 2t, you can immediately find a. If you know sine of 2t, the a is found and the problem is solved because this is a. Okay, so it is your goal. What is sine of 2t? Well, it's 2 sine t times cosine t, if you know this one. But for you, it will be even enough to know what is the sine t times cosine t. If you know this product, you are good to go. So you can solve the problem pretty fast. And that's the main equation that we have. And here we have exactly the product that we need to find. So for us, it's enough not to solve this equation completely, but to only find this product. Well, it's a good idea to separate it. Let's bring it to the right side. And this equation will look like sine t plus cosine t equals 1 over 4 minus sine t times cosine t. And after that, when you have this expression, if you have just minimal experience in trigonometry, you will recognize pretty quickly that now you should square both sides. Because when you have sine t plus cosine t, if you square it, you will have an amazing situation that the sum of squares here will be 1 plus double product. It's a very common thing. As soon as you see this expression, it's very often you just need to square it to simplify the situation. So let's square both sides, and on the left side we'll have 1 plus 2 sine t times cosine t, and on the right side we will have 1 over 16, it's the square of this one, minus double product, it will be 1 over 2 sine t times cosine t, plus the square of the last one, sine t times cosine t squared. And here already you can see that you don't need to drag this big expression sine t times cosine t in the all over. So you can immediately recognize that this is present everywhere, and you don't need to get it in this form. You can introduce some new variable, for example, b, and this one will be simply an equation for b. And if you find b, this is exactly sine t times cosine t, and you will be able to find a. So 1 plus 2b equals 1 over 16 minus 1 over 2b plus b squared. Let's solve this quadratic equation. B squared, this one stays on the left side, and this I bring here, it will be minus 5 over 2b. This one stays here, and this one we bring here, minus 15 over 16 equals 0. Now I don't want to work with these fractions, I want to avoid it. I multiply everything by 16, and the equation looks like 16b squared minus 40b minus 15 equals 0. It is a simple quadratic equation for b, and if I want to solve it, I just write discriminant equals 40 squared is 1600, and minus 4 times this one times this one, so it will be plus 4 times 16 times 15 times 16. 4 times this one times this one. 4 times 15 is 60, 60 times 16 is 960, 960 plus this one will be 2560. And of course, you can immediately notice that 256 is a power of 2, which is a great thing. So it will be 2 to the power of 8 times 10. It's like a very good sign that you have a discriminant like this. Probably it means that you are on the right way, if the discriminant is a good number, not something terrible. But here is a good situation, and square root of d equals 2 to the power of 4 times square root of 10, which is great. So now b equals 40 plus minus 2 to the power of 4 square root of 10 divided by 32. Okay, and here let's write it like this. 40 plus minus 16 square root of 10 divided by 32. Immediately you can notice that it makes sense to divide everything by 8. So we will have 5 plus minus 2 square root of 10 divided by 4. And what personally I would do, I would like separate numbers on the top, and I would have like one value of b. For example, b1 is 5 over 4 plus square root of 10 over 2. It just separated it, and so you obviously understand what's happening here. So, and b2 equals 5 over 2 minus square root of 10 over 2. Here are two possible values of b. Let's go back to our substitution. We remember that b equals sine t times cosine t. So it may be that some of these numbers will not work for us. And how to understand which of them will not work for us? Well, this one is simply sine of 2t over 2. It is a sine of some angle over 2. Sine of 2t is in the range from minus 1 to 1. So if sine of 2t is in the range from minus 1 to 1, then sine of 2t over 2 is in the range from minus 1 over 2 to 1 over 2. These are possible values for this one. So if we want to find an appropriate value of b, it should be in this range. So one of these numbers will not work for us probably. And of course it's this one, because this one is larger than 1, it's not in this range. And this one is exactly in this range. It means that sine t times cosine t equals 5 over 4 minus square root of 10 over 2. And let's remember our golden equation that we had here, that this is an equation where we can find a. So sine of 2t is exactly double of this one. So it means that 2 times 5 over 4 minus square root of 10 over 2 equals, and on the right side we have a minus 3 over 4. A minus 3 over 4. Great. So on the left side, 5 over 2 minus square root of 10 plus, we bring here 3 over 4, plus 3 over 4 equals a. And from here, we can tell that a equals 3 over 4 plus 5 over 2. Instead of 5 over 2, we write it as 10 over 4. It will be 13 over 4 minus square root of 10. Okay, it is our value for n. 13 over 4 minus square root of 10. So, and we needed to find the value of this expression. We denoted it as a in this form. This fraction, m and n are coprime numbers, and minus square root of k. And it is exactly what we have in our situation. It is exactly what we have. Here, this one is m, this one is n, and this one is k. And m and n are obviously coprime numbers. And you needed eventually to find what is m plus n plus k, which is 27. And 27 is a correct answer for our problem. And this is it for today. Thank you.